Hello, everybody. My name is Byung-jo Choi, an emeritus professor here at Gyeongbuk National University, and I have been teaching the power electronics to my students using this book as the textbook. Okay, I divided the content of this book into 20 topics, and from the last September, I started posting the videos on this YouTube site. So I posted this topic number 4 for converter and so on, and I'm somewhere here. So this semester, I'm posting the lectures about this control scheme of a PWM converter, voltage mode control, and the current mode control. So now I decided to upload my previous lecture slide regarding the basics of PWM power conversion. Topic number 1, PWM power conversion, and topic number 2, power stage component, and so on. Okay. So actually, this video have been taken 3 years ago, but now I'm posting this lecture video. So the first topic is the PWM power conversion, and the first lecture is titled with basic concept of PWM power conversion. So in this lecture, I was discussing the PWM power conversion in time domain and the SPDT switch and the output regulation using the PWM scheme. Okay, so I'll be talking about the details about this topic in the following lecture slide. Chapter 1 of this book it covers the basic concepts of PWM, DC-DC power conversion, right? So basics, not basics, basic concepts of PWM, DC-DC power conversion. And let me go back to the previous page. So we are dealing with PWM converter, and the counterpart of this PWM converter is what? As resonant converter. Okay, there are 2 types of converter: PWM converters and resonant converters. So resonant converters, we studied this in the last semester. So it's rather complicated and difficult to understand, and also difficult to teach, because that technique is not fully developed yet. That means this PWM DC-DC power conversion or PWM DC-DC converter is fully investigated. So everything is known, right? So this converter is fully matured. Okay, so this one is very, very systematic. Okay, so everything is discovered by some researchers, and I have full knowledge about this, not 100%, but very good percent of this part. But resonant power conversion is not fully understood yet, all right? Particularly the dynamics and control is still under development. Still there are people working on that topic, so that topic is not fully matured. Okay, so it was not easy to teach or to learn that topic, but this one is different. Everything is finalized. So we only discussing the known and the concrete result of previous analysis, and these resonant converters are under matured. Okay, so we discuss the basic concepts of this converter, this power conversion. So let me take one example. This is the example I'm using all the times when I introduce the techniques of PWM, power conversion. So I used this for the undergraduate courses, and I used the graduate courses, and I used this example for the industry peoples. Okay, so let's assume this. So we are trying to energize this string of the diode. So this is LED, light emitting diode strings. So 4 of them are connected in series, and the load is this one. It requires exactly 12 volt. That is the assumption. Practically, there is no such a requirement in practice. But let's assume this works at this voltage at exact 12 volt, and the source of this DC source is batteries with variable out voltage. You know, this maybe typically this is out voltage of this battery is 24 volt, but depending on the status of charge and some environmental things and temperature, the voltage will be varied from, for example, from 18 to 30 volt. And we want to regulate this voltage at 12 exact, all right? So this is battery, and this is LED strings. So in between, we need something, okay, that controls the voltage. So we are using this variable resistor. So it's called conventional resistive solutions. So assume this is the variable resistor, and here is just some branch, and this is the controller. And we assume this current is negligible. So controller is taking the almost the zero current. So I through this controller is negligible. Okay. Then this is the resistance of this LED thing, and this is the RX variable resistance, and this is the RD of resistance of thing. Then controller is this. This is the simple voltage law here. So our voltage across this diode string is, this is a voltage division, this is a battery voltage, this voltage should be 12 volt. Okay, so if this voltage, the battery voltage is increased from the previous value, then this one is increased. Okay, then this one should increase too, right? So the voltage drop here is increased. So the difference between this and this becomes this. So this will maintain at 12 volt. Okay, this is very simple, right? And actually, you have seen this device is called voltage regulator. Looks like this. So it's written here 7815. All right. Then this this terminal is A, B, C, and there are 3 terminals A, I don't know, B, C. All right. Okay. So it senses this voltage here is larger than this. Then increase resistance here, so increase voltage drop to make this voltage regulated at 12 volt, right? So this is the principle of this. Actually, you are not using this variable resistor, so active device works as variable resistor in linear region. Okay, you have seen this. You are using this a lot. Okay, but this is good. But this is basically this resistive solution, and it has very serious power loss problem. For the small power application, it's okay. But for the large power, this power loss can be very large. Okay, so ohmic loss at Rx here is PIN minus P out, and this is IO as current through this battery and this LED string. Okay, this is VB, so input power. Output power is current is the same because this controller current is negligible. So this is the power loss at Rx is the difference between this and this. This is written here, right? This loss is proportional to this current. Okay. So if you use large current, then loss will be large, and it is also proportional to the voltage difference between this and this, right? So there are some technique to reduce the voltage difference between input and output. It's called low voltage regulator. That is basically this resistive approach. Okay, so let me take one example. So problems of this resistive solution. So let's assume this is a diagram of previous resistive solution and operational. You are trying to evaluate the efficiency of this system. So operational condition, assume battery voltage is 30 volt and the power through this LED string is 60 watt at 20 volt. Across this 4 LEDs, the voltage drop is exactly 12 volt. Then this is our power. Then current is 5 volt. Okay. Then power loss is IO is 5M and IO is 5M. This is voltage difference. This is power loss. Okay. So this power loss 90 watt is even larger than the rated power of this LED. Okay. So efficiency is less than 0.5. So this cause huge problems for some applications. Right? Every power loss should transform to the heat. Right? And heat should be removed, properly removed. Otherwise, heat will continue to increase until it destroys the semiconductor devices. So cooling system is required, but the cooling system usually consists of some fans and heat sink, which increase the weight and the size of the LED drive circuit. All right. The primary concern here is power consumption. Saving of power is not a main matter. All right. So the main matter is compatibility of this converter with your electronics, portable electronics. Suppose this is cell phone. So if the power supply of this cell phone is as heavy as this one, nobody will use this. All right? So they are not comparable with modern portable electronics. But this previous, we have another alternative solution. Then their efficiency can be 100%. Ideally, that is fully comparable with any portable, small size or low profile electronics. Okay, so this is big problem in the space power system. We'll discuss the space power system very shortly. Okay. Very small part of that later, all right? So you cannot use, mostly we cannot use this, but there is one particular application, still this resistive approach is used, that is what? Audio amplifier. So the audio amplifier should reduce any ripple component, harmonic component, or any noise it generates harms, okay? So for the quality of the audio, still they are using this type of power supply. So they are heavy, right? And big, okay? So we have alternative solution here. The situation is the same as the previous resistive case, but in here, we have this part and LC between this barrel voltage and this LED string, the load, right? And here is also controller. So it is a little bit complicated compared to the previous resistive approach, but it has biggest advantage. Okay, so this part is called SPDT switch, single pole double throw switch. Let me put this here. Okay, so this is a very, very important device. So details about this is coming later. So assume this for the fixed switching period TS. This switch is connected to this. Okay, maybe this terminal will be referred to as A, and this terminal is referred to P, right? And during the fixed TS switching period, this switch is connected this port A through A for T on, and it is connected to P passive through for the remaining part, right? So the voltage here is something like this. When this switch is connected to the A, this Vx is the same as Vb. When this switch is connected to this passive terminal, it becomes 0. All right. So this is pulse waveforms. So this DC voltage is converted to the pulse waveforms, and we have LC. You have some resistance here. Then it consists of low pass filter, LCR, low pass filter. So low pass filter is just filtering out this voltage, and the average value of this will be generated here, right? So this DC voltage is converted to another DC voltage. Okay, this is the basic principle of PWM converter. So we discuss this little bit further. So first, frequency domain analysis. Let's consider the frequency domain analysis. So this is a periodic waveforms. So Fourier series of this contains the DC component, and is a 0, and fundamental component, and second harmonic, third harmonic, so on. Okay, so omega S to omega S, there is distance here. And omega S is this one, switching frequency. So 2 pi divided by TS. TS is the switching period. Okay. So if this filter is ideal, that means this L is infinite, or C is infinite, or both of them are infinite. Then you have this kind of filter characteristics. Okay, so only this DC component is passing through this. From here, pass from here to there, unaltered. Okay, so this is the ideal case. But in practical case, this will like this. This is the real low pass filter. Then there is this component part of this higher order harmonics will pass through. So this is practical case. Okay, so this is the time domain interpretation of ideal case and the practical case. All right. So let's think about the time domain. Let's think about everything in time domain. Okay, so voltage here, Vx is coming here. Okay, then Vx is this one. In time domain, this low pass filter is just taking average value of this pulsating pulse waveforms. So for the ideal case, this average value of this DC value will immediately appear as the output voltage. So this is the ideal case. All right. But in reality, if this value, they are not infinity, these values are not infinity, then output voltage will follow this during this time period. So, okay. During this time period, it follows this, follow this, follow this, and follow this. All right. So eventually, it will go something similar to DC, but not perfectly DC. Okay. So this is the voltage waveform for the practical case. So this is for the practical case. That is shown here. It's called the ripple component. Okay, so you know the ripple. This is the surface of some pond, lake, and if you see this in distance, it looks like a horizontal line. But if you approach to this part, there is just some ripple component, something like this. Right? So we try to minimize this as small as possible. Right? So this is called two-step. Actually, there are two steps in DC voltage conversion. First one is conversion of this DC voltage into this pulse waveform, and second part is just filtering out this. Okay, just taking the average value of this. Or just taking the DC component in Fourier series expansion. So this one is that simple. And the control law is, you want this one as constant as possible with the minimal ripple component. So our voltage is almost DC, and that value is average value of this voltage. And we use overbar to represent the average of something. And this is the average weighting factor, because this is the TS, and it has this value only, this period. So weighting factor. It's called Dury ratio, Dury cycle of active switch. Okay. Some student, particularly Korean student, they call it ratio. Ratio is something else. Okay? No. They call it Dury. Okay? Dury is something else. Dury ratio. All right? So you should call it Dury ratio, not Dury. Dury ratio of active switch. Then there is no power loss. Okay? So in here, there is no power loss because if SPDT switch is ideal, there are no power loss, and this reactive component, if they are ideal, does not take any power. So in theory, this efficiency is 100%. Then all the problems associated with power loss, okay, heat generation and requiring of the heat sink and some fans, they are gone. All right. So this one is fully compatible with modern electronics. So you are using this. Okay. Some details about the SPDT switch. Okay. SPDT switch is acronym for the single pole double through switch. There is a pole. Okay. Pole is moving here like this. There is one pole, and this through may be considered pass. There are two passes, single pole, double through switch. All right. So A is called active terminal. Let me use this purple one. Active terminal, and P is passive terminal, and this one is called C, denoted as C, referring to common terminal. All right. Okay. This is just the symbol of this one. So, and this is the practical implementation of this SPDT switch using this semiconductor switches. This is N-channel MOSFET, and this one is a diode. So we will discuss some details about this. But now assume this, there is some voltage source across this A and P terminal, and there is a current source as connected here, right? And this is gate source drain of MOSFET, and the VGS is voltage across gate and source. Is this one is gate drive signal. VGS is during this period of time, this value is very high, and during this period of time, this value is 0 or negative or very small. So we use 0 for this. Okay, so it does not mean during this voltage is 1 and this voltage 0. It means this is the high voltage, sufficiently larger than threshold voltage of this, and this voltage is negative or 0 or smaller than threshold voltage. So when this VGS is denoted as 1, and when VGS is denoted as 0, there are two situations. Then MOSFET is turned on because channel creation. So MOSFET is on. Then this VS reverse bias this diode. So diode is turned off. All right. When this VGS is 0, okay, VGS is smaller than threshold voltage of this N-channel MOSFET, then this path is cut. Then this I turns on this to maintain continuity of the current. Okay, so this is called freewheeling. Will be discussed that later in detail. So when VGS is 0, MOSFET becomes off, diode becomes on. All right. So I wrote down here, SPDT switch contains one pole which is always connected to one of the two possible contacts through A, through B. Okay, so this is impossible. It cannot hang in the middle, so it should be connected to this one or this one. This is just symbolic illustration of this switch. Okay, and usually SPDT switch is implemented MOSFET and diode. In the past, they used something else, but we are using this particularly for the speed of operation. So this SPDT switch is playing a critical role in PWM, DC-to-DC power conversion. Let's discuss the PWM, basic features of the PWM, which is very intuitive and very easy to understand. All right. So you have this part. This is the part of previous circuit, and so Vx is this one. So this voltage is 0, and this voltage is 24 volt. All right. So this output should be regulated at 12. Then duty ratio of this should be 0.5 to have this. Okay. So suppose this is 10 microsecond, and this period, this period is called on-time period, because during this period, MOSFET is turned on, diode is turned off. Then this is obvious, so obvious. Twelve volt. Now this voltage VB, battery voltage is increased from this one to this. Then you should reduce this on-time period. So T on prime. So now T on prime is only 4 microsecond. Then 4 divided by 10 times 30 is 12. So controller is so simple. So this one, this is our voltage. This one, our voltage should be the same, right? So this product should be the same. As can be considered the basic law in the PWM converter. So this is called pulse width modulation. Modulation means what? Something is changing. You are changing the width of this pulse to have this average value of this voltage be identical for two different cases. That is called PWM. So this is the most popular scheme for the DC-to-DC converter, simply because the simplicity of this operation and easiness of analysis and modeling. Okay. You have another one, resonant converter, which is rather complicated to analyze and to understand, right? To design. So this PWM is the prevailing techniques for the PWM converter at this current moment. Okay, so let me summarize what we have discussed so far. So this is the definition of PWM power conversion. There is a voltage source which can be varied in magnitude, and this is some load. We are using some resistive load, but this is not practical case. Anything can be connected here. Okay, so this resistive load is purely imaginary things. All right, so nobody will use this resistor as a load except some special case. Okay, this topic will be discussed in the later courses. Now we assume a pure resistor as a load, and the things in between is called PWM conversion circuit or PWM converter. So basic principle is this DC is converted to these pulsating waveforms, and using this LCR, low pass filter, including this, so load functions as the part of low pass filter, and our voltage will be average the value of this, and with some ripple component because of the non-ideal characteristic of this low pass filter. All right, so it's called two-step DC to DC power conversion of DC voltage into a pulse waveform Vx and filtering the pulse waveform into another DC voltage VO, okay, control law. This average value of this should be constant with small ripple component, okay. It's so easy and so obvious to understand, all right? So we discussed the PWM, this converter, but somehow I'd like to summarize the terms used in here. So power conversion means changing the form of electrical energy power from one form, originally given form, to another form, the desired form, okay, using electric device, all right? So it's called power conversion. We are not talking about some mechanical things, so we are talking about the electric devices are used during this power conversion. And power electronics is electronic engineering dealing with all types of power conversion. But most important thing is we are not allowing any power loss theoretically. That means you are testing the maximum possible power conversion efficiency of 100%. Okay, that is not possible. So we are trying to minimize power loss as low as possible, right? Then we need switching, okay? So we are doing switching to reduce the power loss. Okay? Otherwise, it increase the power loss dramatically, then that becomes useless, right? So power electronics. So previous that alternative solution using SPDT switch and low pass filter is good example of power electronics, but resistive solution is not classified so. So it's not a power electronics because there are huge power loss, right? And this power conversion is, there are many types of power conversions, but especially changing the level of DC voltage is called DC to DC power conversion. If you use the PWM technique, not resonant technique, then that power conversion is called PWM power conversion. Okay. This shows some different type of power conversion. So basically you have AC and DC. So this is AC, right? So sometimes we need DC from AC source. Then we use what? Rectifier, okay? Diode rectifier, simple diode rectifier, and sometimes we use power factor corrected rectifier, but they are rectifiers. So we rectified AC and converted into DC, okay? So in terms of the frequency domain, there is some frequency here, but frequency becomes 0, okay? We change the DC and we are changing this DC to another DC. What we are changing? Amplitude of voltage, okay? You are changing in magnitude, okay? So this is the DC power conversion. And if we use PWM technique, not resonant technique, then that called PWM DC to DC converters. So we converted DC to another value of DC. Sometimes we need to change DC to AC, all right? Then this process is called inversion, and the circuit performing this inversion is called inverter, okay? You are using the term inverter or inversion. Why this is inversion and why this is just conversion? What is the difference between inversion and conversion? In the past, for the most applications, power is coming, this AC, and people used this rectification. So this power conversion is normal or forward direction, regular direction, and the DC from and they found some need to convert DC to AC. That process is inverse process of this one. So they call it inversion. Okay. So DC to DC conversion, no DC to DC inversion, right? So DC to AC DC conversion is inversion, okay? And there is AC, so we need to change to another AC. What we change? First one is what? Magnitude and frequency, all right? Magnitude change is easy. Transformer is doing job for you, but the changing the frequency is very complicated, difficult. It's called conversion. Cycle conversion. So when we are talking about the AC to AC conversion, we mean the changing the frequency of AC, right? Cycle conversion. This whole process, these four processes are collectively called conversion. Okay, so if when you are referring, you refer to power conversion. So this whole things, if you refer to DC to DC conversion, just conversion means this DC to DC conversion and PWM conversion or resonance conversion. And later on, we will be discussing only this part in detail. All right? Okay.